Section 5.3, Graphs of Polynomial Functions. We have the definition of a polynomial function here. With n being a non-negative integer, a polynomial function can be written in the form f of x equals an times x to the n plus an minus 1 to the xn minus 1, and that degree begins at n, that is the degree of the polynomial, the highest exponent, and we go from that degree down all the way to an x squared, an x, and potentially a constant term, where each one of those ai's, each one of those values, a sub n, a sub 2, 1, or 0, all of those are constants. They're coefficients, as we call them, and they can be any real number. The only restriction is that the first is our leading coefficient, and it cannot be 0. So each expression of this, the an x to the n, the a2 x squared, etc., those are terms of our polynomial function. Now, we discussed in section 1.4 polynomial operations and some properties of them, so if you feel like you need a refresher on what those are and how to work with them, you might go back and check that section. Polynomial functions of degree 2 or higher have graphs consisting of smooth curves. Okay, the big two characteristics of polynomial functions are the continuity that comes from them being smooth and not having sharp corners. Okay, that's what smooth actually means. No sharp corners and continuous. So we want to use that description to look at each of these. Which of these represent a polynomial function? Well, easier thing is to eliminate functions that don't match that description. The first of which is g of x here, which is actually an absolute value function. It has a sharp corner, so that is not a polynomial. K of x, bottom right, that has a break. Okay, it is not continuous. However, these other two, f of x and h of x, are both polynomial functions because they are continuous and smooth curves. Now, I probably should say that it's not true that every smooth curve is a polynomial. Okay. They can be represented by polynomials in a sense that you actually see later on down the line. But polynomial functions, so perhaps this question should actually say which of these graphs could represent a polynomial function. I'm going to add the word could represent a polynomial function, because those being continuous does not, again, continuous and smooth does not mean that they are polynomials, but they could be. All right, example 2, find the x-intercepts of this polynomial by factoring. Well, first thing we might notice is that there is a common term. Okay, we can factor out actually an x squared. That would leave us with x to the 4th minus 3x squared plus 2. Now, x to the 4th minus 3x squared plus 2, that also factors. Numbers that multiply to be 2, that add to be negative 3. Okay, we're going to have x squared minus 2 and x squared minus 1. And we'll keep our x squared term there. Okay, now finding all of the x-intercepts is where each of these values are 0. So to find out where f of x equals 0, we'll set each of those equal to 0. So x squared equals 0, x squared minus 2 equals 0, x squared minus 1 equals 0. Okay, and actually each of those terms factors more, so let's actually do that first. That will make this a little more clear. Now, these are not integer factorizations. Well, the first one isn't, at least. I could write this as x plus the square root of 2 and x minus the square root of 2. It's not a perfect square, but I can take the square root of that. And then the second is x plus 1, x minus 1. So, setting each of those equal to 0, some of those are very clear. X squared equals 0 is going to be x equals 0. X plus root 2 equals 0. will be a solution of x equals minus root 2. Now, these two together actually allow us to say that x is equal to plus or minus root 2. And then the last one, same idea. X plus 1 equals 0 tells us x equals plus or minus 1. Negative 1, then positive 1 from the second. So there are 5 solutions to this equation. So our x-intercepts are these points. 0, 0, root 2, 0, minus root 2, 0, 1, 0, and minus 1, 0. We have 5 solutions. Now, one thing I'd like to point out here is once you took the square root at this, here we take the square root of both sides, this doesn't actually make much sense, but I'm going to go ahead and write this. I could have written like the other two, plus or minus 0. Like I said, that really doesn't make much sense because 0 is the only number that only has one square root. But in some sense, if you count that 0 twice, there are 6 solutions. So there are roughly 5 or 6 solutions. And the degree of this, the highest exponent, is x to the 6th. That is not a coincidence. The number of solutions is always equal to the degree. That is just a fact that we will actually state later. But it's good to notice that. Next, find the x-intercepts of this function by factoring. Now, this one is a third degree polynomial, and I'm not seeing a greatest common factor. I'm going to go ahead and factor this by grouping. The first two terms have an x squared in common, which would leave us an x minus 5. The second two have a minus 1. We'll go ahead and factor that out. That would be x minus 5. Right, so with our factoring by grouping, that would be x squared minus 1 and x minus 5. So the x-intercepts, if we continue factoring, this is x plus 1, x minus 1. Bring down our x minus 5. Our x-intercepts is where this is 0. So for the first one of those, we have x equals negative 1. For the second, we have x equals positive 1, and then we have x equals 5. Let's write that out completely. So our x-intercepts are the points negative 1, 0, 1, 0, and 5, 0. That answers the question. Example 4 is find the y and x-intercepts. To find the y-intercept, we will set x equal to 0. Okay, so we'll find f of 0, which is 0 minus 2 squared, 2 times 0 plus 3. Right, that would be negative 2 squared, so positive 4 and times 3. Go ahead and write that as negative 2 squared times 3. That's 12. So our y-intercept is the point 0, 12. For our x-intercept, we'll set each of those factors equal to 0. So x minus 2 squared equals 0, and 2x plus 3 equals 0. On the right, we have x equals minus 3 over 2, subtracting 3, dividing by 2. On the left, we just end up with x equals positive 2. So we have two x-intercepts, that is 2, 0, and negative 3 halves, 0. And again, I'll point out, because of that x minus 2 squared, we actually have two solutions there. Even though we have one value, it represents two solutions. So in fact, there are, well, actually 2, 0, we would consider that a double root because of that squared. Okay, so in total we have essentially 3 solutions. However, the 2, 0 is actually representing two solutions as one number. Find the x-intercepts of h of x equals x cubed plus 4x squared plus x minus 6 using a graph. And I've gone ahead and placed a graph here. And by inspection, it looks like our solutions are negative 3, negative 2, and 1. So let's verify that. Let's take h of negative 3. Negative 3 cubed plus 4 times negative 3 squared plus negative 3 minus 6. That would be negative 27 plus 36 minus 3 minus 6. Let's go ahead and verify that. Alright, that is 0. So h of negative 3 equals 0, meaning that one of our x-intercepts, our solutions, occurs at negative 3. Alright, h of negative 2. Negative 2 cubed plus 4 times negative 2 squared plus negative 2 minus 6 minus 8 plus 16 minus 2 minus 6. That is also going to be 0. So negative 2 is one of our solutions. And then last we'll find h of 1. 1 cubed plus 4 times 1 squared plus 1 minus 6, which will be 1 plus 4 plus 1 minus 6, which is going to be 0. So we have 3 solutions, negative 3, 0, negative 2, 0, and 1, 0. And so I'm going to go ahead and write these over here. Negative 3, 0, negative 2, 0, and 1, 0. Those are our solutions. Now we can actually write this function in a factored form, if that'll fit. Actually, let's put that right here. We could go ahead and write h of x equals x plus 3, x plus 2, and x minus 1, because of those 3 solutions that we have. And finding the x-intercepts, that is those 3 points, and that question is finished. Identifying zeros and their multiplicities. Okay, let's go ahead and look at this graph here. Alright, if we look at the solutions here are negative 3, they are 1, and 2. Now what I want to look at is the behavior at each of those solutions. Here we have x plus 3 to the first power. To the first power. If we inspect the graph around that, okay, so ignore the rest of the graph and only look at this section right there close to it. Locally, as in very, very close to negative 3, that graph actually looks like a line. It looks like something with degree 1. Okay, let's consider the next point. We have 2. Okay, that is x minus 2 squared. Okay, x minus 2 squared. If we look around x equals 2, in that little box that I've drawn there, the graph looks like a quadratic, which is a degree 2. Okay, so degree 1, degree 2, and our last point, -1, that solution. If we inspect around that point, then that appears to be cubic, which is a degree 3. So the exponents on each of those solutions, on each of those factors, actually tells us what the behavior is going to be like locally, what the function is going to look like around that value of x. All right, so this is summarized in a little chart on this next page. If the multiplicity, that is the exponent on that term, so here we have this, if we have a form that looks like this, okay, the degree of that factor is going to tell us what it's going to look like. If the factor has a degree of 1, then it's going to look like this. It's going to cross at that point h. If it has a multiplicity of 2, that is, if the exponent, if it's an x minus 2 squared or something of that nature, then at that point, h, it's going to act like a quadratic. It's going to look like a quadratic locally, very close to that. If we have a degree of 3, it's going to look like a cubic. And the higher the degree, it begins alternating between these two. Okay, a 4 looks like this, but it's much closer. A 5 looks like this, but it stays close to the axis longer. Okay, so all exponents, or all multiplicities is what that's called, that are odd act like this. They cross. All multiplicities that are even touch, and they bounce off. And that is where this is stated right here. The graph will touch the x-axis at zeros with even multiplicities. The graph will cross versus touch at zeros with odd multiplicities. Separate fact is that the sum of the multiplicities is the degree of the polynomial, and the higher the multiplicity, the flatter the graph will appear at the 0. So let's use some of those facts here to determine what the multiplicities of the zeros here might be. All right, we have, it looks to be 3 zeros here. All right, so we have x equals -3. We have x equals -1. And we have x equals 4. All right, so what those factors are going to look like: x plus 3. Okay, x plus 3 to some power, x minus 1 to some power, and x minus 4, or plus 1 there, and x minus 4 to some power. I'm going to go ahead and write these as P1, P2, and P3. Now, based on the local behavior, okay, looking around -3, that appears to be quadratic. Okay, it touches, does not cross. So this one has to be, actually let me move that so that label is not misleading. That means P1 is even. Okay, 2, 4, 6, etc. Looking at x plus 1, so that'd be at -1, that appears very straight. Okay, so this one is odd, and it crosses. So that one could be a 1 or a 3. All right, now P3, looking at 4, that curves a bit more. This one is odd because it crosses. So we have an even, an odd, and an odd number that add up to be 6. P1 plus P2 plus P3 equals 6, because this is polynomials of degree 6. Now, a safe guess here would be that P1, okay, that it's going to be x plus 3 squared. Let's just start there. That's the smallest even one we can go with. All right, we could go with x plus 1 to the first power because it does seem very straight. It seems like a line at that point. And x minus 4 cubed because of the way it curves. Now that seems to be the most likely scenario because 2 plus 1 plus 3 is in fact 6. So here are my solutions. Okay, that's definitely the case. And our multiplicities appear that they would be 2. Let's go ahead and call this f of x. Be 2, 1, and 3 respectively. So there is our function. Now, one thing is actually missing here because we should have an a term, okay? Because this question doesn't ask us to find the equation for that, I'm going to leave that general. I'm going to say it's a, and we'd have to figure out what that is. There's a separate step to figure out. We'd use 1 point to do that, but let's just go ahead and move on. For our next question, we want to identify turning points of a polynomial function. All right, but first we'll need to use this, finding the end behavior. So the way a function looks, okay, the way that the graph looks, if it's an even degree versus an odd degree. So an even degree is going to look like a quadratic. I'm going to draw a separate chart over here. Do that. We'll go with even. Okay, this is just going to be a little sketch. Even degrees look like a quadratic that opens up or down. I'm just looking at the ends here. Okay, opening up, we know that that's the case when the a term, the leading coefficient, when that is positive. We know that it opens down whenever the leading coefficient is negative. Now we have said already that a cannot be 0, the leading coefficient cannot be 0. All right, so for odd degrees, these are going to look like a line, okay, increasing from left to right if a is greater than 0, and decreasing from left to right if the leading coefficient is negative. Now these pictures actually show similar things, but I feel like this might be helpful as you're looking at your notes and going back to look at these. All right, so these are written out in limit notation. As x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x goes to infinity. Okay, these are the precise ways to write end behavior, which we may come back and use at some point. So you might read over those, see if they make sense, and then we can continue going. All right, a turning point of a graph is a point at which the graph changes direction from increasing to decreasing, rising to falling, or decreasing to increasing, falling to rising. Now, a polynomial of degree n will have at most n minus 1 turning points. So let's determine these very quickly. All right, the degree for part A here, the highest exponent is actually an x to the 5th. So turning points, okay, so the maximum number of turning points is 4. This function could turn 4 times. Now it might not have that many, but the maximum number it can have is 4. All right. For part B, all right, the degree is what we need to find first. Now think of our properties of exponents here. All right, the first factor has a degree of 2. Okay, we have a degree of 2. Our second also has a degree of 2. And based on our exponent properties, that would mean together they have a degree of 4. We'd add the exponents. So if the degree is 4, the maximum number of turning points is 3. It could have at most 3 turning points. Now let's use all this information we have gathered so far to sketch the graph of f of x equals -2, parentheses, x plus 3 squared, that quantity, and then we have a factor of x minus 5 as well. All right, let's sketch this. So based on our end behavior, we need to know our degree. All right, so our n is, let's see, we have a second degree polynomial here, that's squared, and a first degree. So in total, we have a degree of 3. All right, now let's go ahead and make note of our leading coefficient. Our leading coefficient is -2. All right, so we have an odd degree with a negative leading coefficient. So based on our end behavior diagram, okay, so the first thing we're looking at is the end behavior. This function is a cubic with a negative leading coefficient, so it's going to look like this. It's going to be decreasing from left to right. Now we don't know how many times it turns, things like that, okay? So let's go ahead and move on to the next thing, which is our x-intercepts. This whole section was leading up to sketching a graph, really. All right, x-intercepts is where we set the factors equal to 0. So I'm going to go ahead and jump to that. X plus 3 squared, x minus 5. We don't have to worry about the -2 because it's a constant. Okay, it's not going to affect our zeros. But just in case you'd like, there it is. So we'd set x plus 3 equal to 0. Now notice there are actually 2 of those. X plus 3 equals 0, x plus 3 equals 0, and then x minus 5 equals 0. Because that x plus 3 has a multiplicity of 2. It gets me a double root there. So this is x equals -3 and x equals 5. All right, so we have our x-intercepts. 3, 5, 0. Now for our y-intercept, evaluating that at 0. So f of 0 is -2, 0 plus 3 squared, 0 minus 5. So that'll be a -2 times 9 times -5. So that is a positive 90. Positive 90. All right, so I'm going to go ahead and sketch that in this upper corner. And by sketch, I really mean sketch. This is not drawn to scale. So I have solutions at -3 and 5. Y-intercept of 90, so this is 0, 90. All right, now we know what the end behavior is going to look like. Now we know that x minus 3, or at -3, because of this right here, it is going to touch, not cross. Right? So now we know off in these directions it's going to be decreasing. So that's why I drew it that way. Okay, it's going to come down. It's going to come down, and then it's going to bounce off of that. Go back up. It is going to go up to 0, 90, and then at some point it's going to have to come down by 5, and it will decrease, looking something like that. I highly suggest that you put that in a graphing utility, whether that's Desmos.com or your calculator, and verify that it looks like that. It's going to be a little distorted because of my scale, but it will look something like that. Those characteristics will all hold. All right, the next thing we have here is something called the intermediate value theorem. So if we have a polynomial function, the intermediate value theorem states that if f of a and f of b have opposite signs, that is, if f of a is less than 0 and f of b is greater than 0, one's positive, one's negative, then there exists at least one value between the two a and b values, such that the function itself is 0. If the function is, as this image depicts, if the function is positive, the function is negative, somewhere in there. Now we can't pinpoint precisely where it is, we just know that there is a 0. And that is very important for lots of things that follow. All right, example 9, show that the function x cubed minus 5x squared plus 3x plus 6 has at least 2 real zeros between 1 and 4. Show that it has at least 2 real zeros between 1 and 4. Well, let's first go ahead and see what happens at x equals 1. At x equals 1, that would be 1 cubed minus 5 times 1 squared plus 3 times 1 plus 6, which is going to be 1 minus 5 plus 3 plus 6, which is 5. Okay, f of 1 is 5. So let's go ahead and keep up with what I'm finding over here at the table. If x is 1, f of x is 5. And we know the other endpoint is 4, so we may as well evaluate that. Alright, that'll be 4 cubed minus 5 times 4 squared plus 3 times 4 plus 6. That is 2. Alright, so f of 4 is 2. Both ends are positive. Alright, so let's try the points in the middle. X equals 2. Alright, let's just go ahead and I'm going to work with that. Alright, let's see, that is x cubed minus 5x squared plus 3x plus 6. Looking at my table, x equals 2 is 0. And I need space for 3. Alright. If x is 3, then the function is negative 3. Now, our task is to show that there are at least 2 zeros. Well, I can actually tell you what one of them is. F of 2 is 0, right? So let me go ahead and sketch this as well. All these different representations help us see what's going on. So it's a good idea to use multiple representations to your advantage. So 1, 5 is this point here. 2, 0, 3, negative 3. Let's go ahead and put that 3 here. And 4, 2. So our function between those points is continuous because it is a polynomial. Looks something like that. So there are 2 real zeros because there is 1 here, and there has to be 1 between 3 and 4. Alright. We've already discussed this briefly, but the factored form of a polynomial, if we have horizontal or x-intercepts at x1, x2, all the way to xn, then the polynomial can be written as a x minus 1 to the p, 1, x minus x2 to the p2, etc. Our intercepts tell us the factors, which, like I said, we've used this fact several times. So what we're going to do is find the formula for a polynomial based on those intercepts. Now we can find the multiplicities based on the behavior. All right, now I'm going to go ahead and tell you a few things though. Okay, we'll make some assumptions. All right, first off, this is a fourth degree polynomial. I'm going to go ahead and tell you that. All right. We can actually go ahead and say our a value, our leading coefficient, is positive because the end behavior, okay, it's increasing in both directions. All right, so we have some solutions. We have x equals -3, 2, and it appears to be 5. So our factors, go ahead and write our equation. We're going to have a times x plus 3 to some exponent, x minus 2 to some exponent, and x minus 5 to some exponent. Based on the local behavior, these two appear to be linear, and that one appears to be quadratic. So at 2, we have a multiplicity of 2. I'm going to go ahead and say we have a multiplicity of 1 for each of those because of that linear fashion in which they cross. Okay, so they cross, so I know it's odd, but because it moves very linearly in that small little rectangle I drew there, I can go ahead and say it's to the first. Now, to find the equation, the one thing we're missing is the a value. The a value. So let's pick another point, not one of our solutions. And a good point appears to be 0, -2. So let's use the point 0, -2. That means our output is -2, and our input is 0. So 0 plus 3 to the first, and we'll go ahead and drop that to the first. All right, 0 minus 2 squared, and 0 minus 5. So that is going to be a times 3 times -2 squared times -5. That is going to be 3 times 4, 12, minus 60. So minus 60a equals -2, meaning that a is 1/30. So our general form for this equation, this polynomial, is 1/30 x plus 3 times x minus 2 squared times x minus 5. And that is the equation for that polynomial graphed. All right, the last example we're going to have is on the idea of local and global extrema, or maximums, local maximums and local minimums. Now this did come up in chapter 3. Okay, this did come up in chapter 3. So this definition is also there, so I'm just going to skim over that. We want to find the highest and the lowest points, okay? And global maximums and minimums mean over the entire domain, okay? All x values, what's the highest and the lowest points. Local maximums and local minimums are in a certain area, okay? The highest point in it around it, or the lowest point around it. All right, so example 11, an open top box is constructed cutting out squares from the corner of from each corner of a 14 centimeter by 20 centimeter sheet of plastic, and then folding up the sides. Find the size of the squares that should be cut out to maximize the volume enclosed in the box. And we'll look at that graph in a moment. So if we have here a 14 by 20 centimeter plastic sheet, okay, we're cutting out the corners. Now, we are cutting out the same amount from each corner. So the way that I'm going to label these is I'm taking out an amount x. Okay. Now we want to find, we were actually maximizing the volume, right? So let's go ahead and write out what the volume would be for this box. Well, the height of the box is going to be x, however much we cut out, because if you imagine folding those flaps up, that's going to be how high or how tall that box is. So there's my height. Now I should probably go ahead and say this is length times width times height. Our height is going to be x. Here, I'll put it down here to match with the form you're probably used to. Now the length of the box is going to be 20 minus 2x. It originally was 20 centimeters, and we took out a length of x here and a length of x here. So 20 minus 2x. Same thing with our width here. It originally was 14. We're taking out x and x. So 14 minus 2x. That is the function for volume. Now what I want to find are the maximums. Okay, so the zeros, I'll just go ahead and tell you. X is 0. Okay, that's coming from this right here. Another intercept is going to be 7 because that's the value that will make this 0. And another value is 10. 10 will make this factor 0. So I'm skipping a little step there, setting each one of those equal to 0 to get those values. Now, we could go ahead and sketch the graph ourselves. However, I would like to appeal to technology. And this is the graph of the volume function. Okay. V of w, they use w instead of x's there. It's the graph from the textbook. So we have our x values and we have our volume. We want to find the maximum volume. That appears to be this value right here. Right. And having anything from bigger than 7 doesn't make any sense, because then you actually have a negative volume. That's because if this x is bigger than 7, then this side doesn't exist. If it's bigger than 10, this side doesn't exist. So our maximum is going to be at that point. Now, based on technology, okay, I find that the maximum point is approximately 2.7, 339. That is the point. That means we have a maximum volume of 339 cubic centimeters with a corner. Let's just go back and write that again. With a corner size of about 2.7 centimeters. So if we cut out a square of size 2.7 as its width and 2.7 as its length, then we will achieve that maximum volume that we are after. Alright, so there are there are several really important things in this section. Okay, we've got one, the idea of end behavior. Okay, the idea of factoring, local behavior at our solutions, the intermediate value theorem, turning points, the degree. Make sure that you're familiar, okay, that all those terms make sense. And I would suggest putting all of these concepts on a note card or something. I mean, seriously, all these ideas of how you determine turning points, the x-intercepts, the intermediate value theorem, those different things, put them all in one place so that when you need them, you can refer back to them.